what I want to start today, Mark really set the gold standard yesterday for starting off at an elementary level and getting to interesting things. My goal is to start at an elementary level. I'm not sure if I can get to interesting things. So I want to start with representations of compact Lie groups, about which I'm going to say very little. I'm going to assume this is familiar. I'll just remind you that we have the theory of the highest weight. And we all have our own ways of thinking about the theory of the highest weight, but from my point of view, the theory of the highest weight parameterizes representations of a compact Lie group K by pairs T comma phi, where T is a maximal torus, I like compact groups, or at least compact Lie groups, because tori are honest tori, they're products of circle groups. T is a maximal torus, and phi is a character. I'll call it a linear character when I need to emphasize it's a homomorphism from T to C cross. Bless you. Satisfying some conditions. There's a dominance condition that I'm not going to state. Now, if you're used to the theory of the highest weight, this is almost certainly not how you think about it. You think of the theory of the highest weight as parameterizing representations by dominant elements of the dual Lie algebra. But you can take such an dominant integral elements of the dual Lie algebra, you can take such an element and exponentiate it to get an honest character. And then the torus actually doesn't matter very much because there's a unique one up to conjugacy. But if you really wanted to, if you have this kind of twisted mind, you could think of the theory of the highest weight as parameterizing representations by torus character pairs. Once we have this, we know these representations exist. We know they all arise this way. We've got the Borel-Bach theorem. And this allows us to realize such representations in the space of global sections of a certain line bundle. But I'm not a geometer, and that way of thinking about things makes me nervous, so I'm going to rephrase it slightly. So to say it differently, we're realizing such representations in an induced function space. We've talked a lot about induced representations. I assume it's reasonably familiar, but anyway, I'll write down the definition. And finally, the Weil character formula expresses the character, and eventually I'll get to a fancy pants notion of character, but for now character is just what we think it is. It's the function that takes a matrix, an element of K, applies your representation to it, gets out some matrix, we've got finite dimensional representations, and takes its trace. That's the character, and it expresses this on T as a certain mystery function, 1 over the square root of the absolute value of the Weil discriminant, which I'm not going to say much about here. I'll write it down explicitly in the case that we're going to handle later. But 1 over a certain magic function that controls singularities times assigned sum of Weil conjugates of your parameterizing character phi. And again, this may not be the usual way that you're used to thinking of the Weil character formula. We often write down an explicit square root, or near enough to a square root, without the absolute value, and then the signs that occur in the signed sum are slightly different. But whichever way you think about it, it is possible to write the Weil character formula as 1 over the square root of the Weil discriminant times the signed sum of Weil conjugates of phi. So that's the picture we've got for compact Lie groups. Now I want to ask this fairly natural sounding question. What if I try to do the same thing, except I replace my coefficient field? There's an implicit field R lying around here. What if I replace my coefficient field by the p-adics? So what if I take a p-adic matrix group that happens to be compact, and I look at its representations? Well, the first thing that happens here is you look around and you say, okay, let's write down some familiar examples, let's write down some comfortable examples, and it turns out there aren't any. Okay, now that's a lie, but there are hardly any. Now let's make precise what I mean here. Really, by p-adic group, it's really, really easy to write down compact p-adic groups as long as you're flexible with the definition. For example, you could take the ring of integers or the multiplicative group of the ring of integers in a p-adic field. But that's not what I mean by a p-adic group. I mean the usual thing. G is the group of f rational points of a connected, reductive f group bold G. For me, p-adic does not include characteristic 0. It's just a complete, discretely valued field with that's locally compact, so it means it has a finite residue field. But I am going to include, just in case I forget to say it, throughout this lecture, p is not going to be 2. In the next lecture, p is going to be as big as I need it to be, but for now it's just going to be p is not 2. And G is connected. Reductive. So for example, the ring of integers or the multiplicative group of the ring of integers do not arise as p-adic groups in this sense. The group G0, the Harish-Chandra group that arose yesterday, also is not a p-adic group in this sense. So subject to this restriction, it turns out to be quite hard to manufacture compact p-adic groups. In fact, essentially there's only one family. So basically, all compact such groups come from division algebras. And I'm not going to make precise what it means to come from, but the basic idea is that if you understand representations of division algebras, you pretty much understand the representation theory of all compact groups, compact p-adic groups. So let's keep life as simple as possible. We'll work with the unique quaternionic division algebra. Exactly, almost exactly, what it is over the real numbers. It's the span over our chosen p-adic field F of 4 elements, 1 I, J, K. By the way, I'm going to need a lot of integer indices today, and I might accidentally occasionally make I, J, or K an integer index, and I'm sorry about that, but I'll try not to. Usually it's going to mean elements of the p-adic division algebra, and in the real case, in the real quaternionic case, I squared, J squared, and K squared are all -1, and I and J skew commute. We're going to keep that skew commutativity ij is k is minus ji. But now I'm going to specify different squares. I squared and j squared are not going to be minus 1. Instead, I squared will be epsilon. This is a lift to the ring of integers of a non-square in the residue field. Ring of integers of k, residue field of k. Later I'll stick a subscript d on there and it'll mean the analogous objects in the division algebra. And j squared is going to be pi, which is a uniformizer. So this is the group whose, well, the multiplicative group of d is the group whose representations we're going to consider. It need not be. I mean, in fact, it's going to make almost no difference for any of what I say. All that's really important is that p is not. So this is the group where the multiplicative group of this guy is the one that whose representations we're going to consider. So the first question is, do we have any kind of parameterization like the theory of the highest weight? Before you even ask that question, you want to ask the questions, what would those parameters look like? In particular, how many tori does this have? And if you're a happy-go-lucky, optimistic graduate student, as I once was before the p-adics got to me, you'll say, hey, there's a unique torus here. This is an equally good compact group. It's just over a different field. There must be a unique torus here. But then you cry. That's not true. So unlike in the real case, D cross has lots of tori. Well, lots here means 3, but that's much bigger than 1. So specifically, maximal tori in D cross, modulo D cross conjugacy, are in bijection with quadratic extensions of our p-adic field up to F isomorphism. So there are 3 tori. We have ramified 1 and 2 ramified ones. And it's a result of Corwin-Hao-Moy and these names all got attached at various times, but for now I'm just going to lump it all together and say that this is from the late 70s. That representations of D cross are indeed parameterized by pairs t comma phi, where t is a maximal torus and phi is a character satisfying certain regularity conditions. Now, if you're used to the Corwin-Hao-Moy parameterization, you probably don't think of it this way. You probably think of a parameterization in terms of admissible pairs of a field extension and a character of that field extension. But here we've got that tori are parameterized by field extension, so giving it to us the same as giving a field extension. All right. So that's the analog of the theory of the highest weight, is that if I give you a representation, you can find a parameter corresponding to it, although usually, I guess it was Mark who was talking yesterday about following a bijection in only one direction. Usually we go the other way. Usually we're interested in starting with a parameter and constructing the corresponding representation. So what's the analog of dWd? Well, the most obvious thing to do is we've got a representation, phi, of the subgroup T of D cross, so just induce it up. You can induce from E cross up to D cross. the character phi, and if we were in a happy compact Lie group setting, then this would work, but in the p-adic setting, this is just enormous. This is a huge representation. So what I'm going to do instead is I'm going to extend phi before inducing. And here I've already made some restrictions. I've already assumed that I'm dealing with compact groups. I've assumed that I'm dealing with division algebras. By the way, a division algebra is not actually compact, but it's compact mod center, which is the next best thing for purposes of representation theory. I've assumed that I'm dealing with a division algebra of degree 2, which is a big restriction. I'm going to make a further restriction here for simplicity. I'll talk about how to get rid of all of these restrictions in the next lecture. Today, we'll assume that the extension E over F, this quadratic extension that parameterizes the torus in which we're interested, is totally ramified. Necessarily tamely ramified because I've assumed that P is not 2. But I'm going to assume it's totally ramified. Usually that would add complications. Here it actually simplifies things, somewhat surprisingly. So here's the p-adic fields, as we all know, carry natural filtrations, and because of the way the topology is set up, if you go deep enough in the filtration, phi is going to be trivial. So for n sufficiently big, phi will be trivial on 1 plus the n plus first power of this prime ideal. I'm going to carry around that n plus 1 for convenience because I'm actually interested in the last place where it's non-trivial rather than the first place where it's trivial. Now potentially, if I multiply phi by other characters, I'm going to decrease this n, and I want to assume that doesn't happen. So assume, and this is an easy reduction, I won't go into the details. I'm going to assume that we cannot decrease n by replacing phi by a twist. What do I mean by a twist? I mean if you multiply it by a character of the ground field, inflate it up to E cross phi of the norm. Okay, so potentially if I multiply phi by chi composed with the norm, I'll decrease that n. I do that as much as necessary until I cannot decrease n anymore. Then I've got this technical condition that I suppressed to the point of not even writing that there was a technical condition. It's called admissibility. The admissibility condition of Corwin-Hao-Moy in this setting unfortunately, by the way, admissible here, we're mathematicians, we only know so many words. It has nothing to do with the admissibility of p-adic representations. It just means like okay. The admissibility condition of Corwin-Hao-Moy just means that n is greater than 0. I don't want to deal with a character that is trivial on 1 plus the prime ideal itself. And in our setting, it's automatic that n is odd. There are a lot of simplifications here that are happening because I'm in a quaternionic division algebra. I'd have to worry a lot more about division by 2 in the general case, but there's this machinery of Moy and Prasad that takes care of all that very neatly. I just want to be concrete today. So remember my goal here. My goal is to extend phi. I'm going to extend phi phi already lives on E cross. I'm going to extend it out into the division algebra, E cross times 1 plus the prime ideal in the division algebra to the n plus 1 over 2. I'm going to do it in the following way, and I'm not going to go into the details of the fact that this actually is an extension or that it gives a character, but hopefully you'll believe me. Here's how it works. I can write my entire division algebra as E plus E perp, where this is the perp with respect to the trace pairing. And to be very concrete, if we chose our uniformizer correctly at the beginning, this is just, the E part is just the bit spanned by 1 and J, and the E perp part is the part spanned by I and K. Everything works out very nicely. This decomposition descends to the filtration of D. I can also write any element in the n plus 1 over 2 with, n plus 1, yes, over 2 with power of the prime ideal as an element of E that lives in here plus an element of E perp that lives in here, and I use that to write down my extension. I'm going to define phi hat of gamma, which is going to come from E cross times 1 plus Z, which is going to come from a certain subset of here, to be just phi of gamma. Whenever Z comes from the perp space. I won't go into why this is a very natural thing to do. It might look like a highly unnatural thing to do, or at least it might look like a piece of luck that it works. But from the appropriate point of view, this is actually a very, very natural way to extend. Then if I define V phi to, let me give this subgroup a name. I'm going to call this new compact mod center open subgroup to which I've extended E cross times 1 plus PD to the appropriate power. I'm going to call that K phi. And I'm going to define V phi to be the induction from K phi up to D cross of my extended character phi hat. And just as a reminder, this is the space of all functions, complex valued functions on D cross, satisfying appropriate smoothness conditions, such that f of k times gamma, and here I mean by k, not that k from before, but an arbitrary element of this compact group. This should be phi hat of k times f of gamma, well, k in k phi and gamma in D cross. So this is a certain space of functions on D cross, and this supports an irreducible D cross action by right translation. Far from obvious that it actually is irreducible. It's obvious that it's an action. It's far from obvious that it is irreducible. You have to do some computation of intertwining operators, but Corwin Hamoy did it for us. That's not the point of today's talk. This guy's an irreducible representation. So we've got the analog of the theory of the highest weight. We've got the analog of the Borel-Weber theorem. At least if you're willing to be flexible, you can call this an appropriate analog. What about the Weil character formula? That's what I want to spend most of my time on today. So we don't have a whole lot here. We just have character on a subgroup that we've induced up, and we want to know what its character is going to look like. Our main quantitative tool is the Frobenius character formula, which you're probably used to seeing in the context of finite groups, but this is the next best thing to finite. It's induction from compact open mod center group to compact group. In particular, this is finite index induction. Frobenius character formula works perfectly well. And it says that the character of our induced representation can be expressed as a sum over those elements of D cross mod K phi that actually conjugate gamma into the inducing subgroup. You sum over all those guys the values of the inducing character. What we're going to do is we're actually explicitly going to compute this sum. And I do mean explicitly. The theme of today's lecture is Grundy calculations. The theme of Friday's lecture is too much philosophizing, so at least we have some fun today. All right. So how do we compute this? Well, we have 4 main principles, and I have to look these up in my notes because every time I prepared this talk, I changed my mind about which guys counted as main principles and which didn't. Here are the 4 I settled on. A discrete Campbell, Baker, Hausdorff formula, which is a term that nobody in the world but me uses, so you got to pay me royalties if you use this. What I mean by this is that the map x goes to 1 plus x from the additive group of the division algebra to the multiplicative group, as long as you stay away from -1. This map behaves in many ways a lot like the exponential map. It's almost as good as the exponential map. So why not just use the exponential map, because the power series has p's in the denominator. It might not converge in as big a range as we want, whereas this guy converges. In fact, there is no convergence. This guy is defined in a very big range. And it's almost as good as an exponential map. So that's one of our principles. Another one is we're going to use the idea of induction in stages. What I mean by that is I'm not going to try to leap all at once from K phi up to D cross. I'm going to make an intermediate stop along the way where the character is easier to compute. The third principle is to group terms. If you tried to write down explicitly which elements G actually occur here, in our small concrete case, you could do it. But it wouldn't be a lot of fun. It would be a mess. So what we're going to do, instead of worrying about which terms G occur, is we're going to try to lump together a bunch of terms G in such a way that the sum over that clump is 0. So we're not going to try to control the sum precisely. We're just going to try to clump it up so that most of it goes away. And our final principle, how will we know that a clump of term vanishes? This is the entirety of my knowledge about p-adic harmonic analysis. So don't anybody go out and scoop me now. The fourth principle says that the sum of a non-trivial character is 0. That's the entirety of my wisdom. And based on these four principles, these four pillars, we're going to compute that sum. Let's see what that would look like. So I want to ease us in nice and slow. Here's a nice, easy start. The character theta, this object that we're trying to compute, vanishes off d-cross conjugacy classes that intersect the inducing subgroup K5. Okay. If this sounds interesting, it's because you haven't looked at the Frobenius formula, because if you look at the Frobenius formula, what's going to happen if you're off a conjugacy class intersecting K5 means there's going to be no terms in this sum, and the sum is going to be 0. So this is completely obvious. So if you look at the form of our inducing subgroup, this means that we only have to worry about evaluating the character at elements, because characters are class functions, we don't have to worry about the distinction between being in and being conjugate to that subgroup. We only have to worry about elements that are in this subgroup, which means elements that are pretty close to E cross. I'd like to do better. I'd like to force our elements to be really close to E cross. And here's how it's going to work. We'll do better by inducing not all the way up to D cross all at once, but first to this smaller subgroup, which is E cross times 1 plus the prime ideal. I'm going to compute the character of the result of inducing up to H. So here is my second principle. Principle B says induce in stages. Why did I choose to induce up to this subgroup rather than the infinitely many other intermediate subgroups by A, by the discrete Campbell-Baker-Hausdorff theorem? It's easier to conjugate by elements of 1 plus the prime ideal. And if we're inducing up to this guy and using Frobenius formula, that's all we ever do have to conjugate by. So I've made my life a little easier. Hopefully it'll show up in the character computations.
Sorry, Loren?
Yes?
Did you say that the index is finite?
Yes.
So how can there be infinity?
I promised one false statement. That's right. So we've got this intermediate subgroup along the way. I'm going to write theta, little theta, for the character of the representation induced up to there. I want to try to compute the character of this guy. And my claim is that I can do better than this vanishing result. Namely, I can say that little theta vanishes off conjugacy classes intersecting E cross times 1 plus the nth power of the prime ideal. Notice before I had the n plus 1 over 2th power. So I have nearly doubled the valuation. I have nearly halved the distance to the torus. The fact that this is not exactly doubled, the fact that I don't have an n plus 1 up here, looks subtle, looks unimportant, but it's actually the source of what's called the bad shell. It's the source of the interesting part of Moynihan-Kirillov theory. It's a very important fact that I've just written p to the n rather than p to the n plus 1. So let's see how you prove this guy. I need a little lemma. This should give you a nice flashback to your grad school days. I'm just going to state result after result here. I need a little lemma, but just a purely group theoretic lemma. It says if you have an element gamma that's in 1 plus some power of the prime ideal, but it's not conjugate to something that's closer to E cross. So if I have an element that's as close to E cross as it can get under conjugation, oops, sorry. If it's as close to E cross as it can get under conjugation, then it's actually not just an E cross times this filtration subgroup, it's an F cross times the filtration subgroup. This is a purely group theoretic fact. It's not true for all groups, but it is true for this one, and it's just a matter of writing down conjugation and seeing what happens. It's crucial for this fact, don't say I never taught you anything, it's crucial for this fact that 2 is a prime. All right, so what can we do with this? Well, suppose you've got an element whose whose conjugacy class, whose H conjugacy class does not intersect E cross times 1 plus PD to the n. Then it's an E cross times 1 plus PD to the A for some A. That A has to be bigger than, I just erased it, but it has to be bigger than n plus 1 over 2. Because we already know you vanish unless you intersect that guy. But it has to be smaller than n. So by the lemma, this is a proof of the proposition. So by the lemma, we have that gamma is in F cross times 1 plus PD to the A. It's not in E cross times 1 plus PD to the A plus 1 is true for some A that's at least n plus 1 over 2 and at most n, or strictly less than n, I should say. So what I'm going to do is just what I promised. I'm going to explicitly evaluate this Frobenius formula, or rather the Frobenius formula for induction up to H, and I'm going to show you it comes out to be 0. If H is a typical element of the form that I conjugate by, and the following thing happens. I'm going to take an element of the form H inverse gamma H. I'm going to take a conjugate of gamma, the sort of thing that appears in the Frobenius formula, and I'm going to conjugate it a little more. As long as I make the right choice of x, which I'll write down in a minute, I wind up pretty close to the element I started with, the conjugate I started with, but I've disturbed it a little bit. A bunch of notation there, which I'll explain in a minute. But if I take a conjugate of gamma and I conjugate it further, I land at the original conjugate times 1 plus a commutator. This is what I mean by the discrete Campbell-Baker-Hausdorff theorem. This is the kind of thing you'd expect if you commutated exponentials. Here we're commutating 1 plus things, and it behaves pretty much the same way. We do not have equality. I've truncated this at the second order term. But as long as I choose x in the appropriate place, at least it holds up to an error of depth n plus 1, which, by the way, we constructed things is in the kernel of the character that we're inducing. I haven't said anything about x yet. This is true for x in the n minus ath power of the prime ideal. I'm sorry about this profusion of indices, but you have to be extremely careful about indices.
Why?
And y is the thing that gives you the element gamma. So gamma is a central element times 1 plus y. So what's this mean? Well, remember, Frobenius formula is a sum of character values at certain conjugates of gamma. And I could take those conjugates to be by h, or I could take them to be by h times 1 plus x. This is a familiar trick, right? You've got an element, so you use hard measure type properties, and you disturb your element a little bit, but it doesn't change the aggregate sum. So what this says is that if I compute the character value at gamma by summing over conjugates of the form h times 1 plus x, I'll get the same answer as if I sum over conjugates of the form h, but I'll have this extra factor 1 plus the commutator of y and x floating around. Right, mod. But no, this is literally true. This is true on the next. All right, and so you cancel both sides, and that says that this guy is 1. Well, okay, so this means that actually what's most likely is that the character value is 0 unless so that this non-linear character value is 0 unless this linear character value is identically 1 for all x. Okay, simple-minded ideas here. And I don't have to worry in the least about which elements h actually occur in this sum. All I care about is that if I've got a single element h such that h inverse gamma h lands in k sub phi, then I can multiply it by 1 plus x and the conjugate by that translated guy still lands in k sub phi. I'm suppressing a lot of details, but you can work them out yourself. I suffered, you should have to. And it's also, it's no fun. So it's much more fun if you just believe it. Now I'm going to write out a computation here. I'll do it once so that you know you can trust me, and after this I'll just say do it, and either you'll do it if you're very bored, or you'll just trust me. If y looks like r plus si plus tj plus uk, and if x looks like r prime plus s prime I plus t prime j plus u prime k, this is what elements for quaternionic division algebra look like when we commute. We get the following object. Well, the r and the r prime go away because they're in the center. If you want to get a term that looks like I, you have to multiply a j term and a k term. It's got to be 2 t prime u minus t u prime. Don't bother copying down the exact form. I just want to give you some feel for what this would look like. That's the coefficient of I in the commutator. To get a j term, you have to pair an I term and a k term. So it's going to look like 2s u prime minus s prime u times epsilon j. And to get a k term, you have to pair an I term and a j term. So that looks like 2s t prime minus s prime t. And for all that Mitya knows, and he's going to spend the rest of the lecture worrying about it, I flipped a sign somewhere. But it doesn't matter. The point is that you have some formula like this. But remember, our definition of phi hat ignored everything that's happening in E perp. That means everything that has an I coefficient or a j coefficient. So we only care about this part for E hat? Sorry, for phi hat. I can throw away all the rest and get the same character value. So given this explicit computation, you don't have to do this explicit computation in general, but we can do it for quaternionic division algebras. So why not? So this shows this term fills out all of the depth n elements, or depth n over 2 if you take account of the normalization properly, the depth n over 2 elements in E as x varies there's only one way that could fail, and the only way that could fail is if y, which a priori comes from pd to the a, if it were actually a little deeper, if it lay in pd to the a plus 1 modulo e. But that would mean that gamma was very close to the torus, very close to E cross, which it isn't. This kind of computation, this kind of manipulation to push elements up and down by conjugation is exactly what I mean. It's how you evaluate everything to do with the character formula. But this is, believe it or not, this is a particularly simple case of it. Well, why is this so decisive? Because since y is not here, that means that these commutators do fill out all of pe to the n mod pe to the n plus 1. But by assumption, phi hat, which is just an extension of phi, is not trivial on 1 plus pe to the n, which means this isn't always 1, which means that is 0. Giant consequence. My students in my calculus or algebra classes got scared by that end of proof box. So to stop scaring people, I make up a different end of proof. So remember, all this was for this partially induced character, this inducing up to this subgroup H intermediate between K phi and D cross. You all remember the notation exactly. There will be a quiz. And what we found was that this partially induced character vanishes at outside conjugacy classes intersecting a very small range. Well, now apply Frobenius formula again to induce the full induced representation from this partially induced guy. Now the only terms that will light up in the full character formula are ones with conjugacy classes intersecting this guy. So it's an easy corollary.
Excuse me, now
Yes.
are you assuming that E is unramified extensor?
E is ramified. Is that all right? Or did I say something that relies on?
You said it was unramified before.
Everybody go back and cross out done. Okay. Mitya says I said totally ramified.
So where are
Maybe un sounds like totally. Yes.
So where all are you using that is totally ramified here?
I'm not using it very much. Pretty much this entire thing is, well, okay, so part of it is in the details that I've swept under the rug. Like I just claimed that this guy fills out all of PE to the end. And you have to say, well, what does that mean about where S is? What does that mean about where U prime is? You have to actually count the depths. And if E is ramified versus unramified, that'll mean different things about where these guys are. So there's a little bit of formal difference in the calculation, but the real big qualitative difference comes from this fact that I said earlier that our N that measures how deep you have to go before phi is trivial, that has to be odd. Which doesn't sound like much, but what it means is that we get no Bay representation occurring. So that's the main reason I'm making this restriction, is I don't want to worry about the Bay representation today. Yeah, I'm sorry if I said at some point that it was unramified. I meant
Ramified is fine.
yeah. All these lemmas are still true in the unramified case, just the proofs will look slightly different. Everything relies on having degree 2. If I replaced it by degree 4, for example, I'd be in trouble. Now I'm going to give you another group theoretic result. I started with earlier this fact that if you are close to the torus, close to E cross, then you're actually close to the center, close to F cross. I never said it, but the center of D cross is F cross. Yes, sir. Oh, you're right. Stephen taught me never to erase anything. The corollary is that our big character, big theta, now vanishes off conjugacy classes. D cross conjugacy classes intersecting. E cross times 1 plus p-adic. So this is pretty good. Previously, we only knew that we could vanish off conjugacy classes intersecting E cross times 1 plus p-adic to the n plus 1 over 2. And I promised you that it's very significant. Every little bump we can give to that exponent makes a big difference. But still, if I asked you to describe those conjugacy classes, bless you, you'd be a little bit unhappy. So I want to give you a refined version of this lemma. I'm going to repeat my earlier summary of this lemma. This lemma says, if you are close to E cross, if you are close to the torus but not too close, then you're actually close to the center. Now I'm going to rephrase it differently. I'm going to say, if you are close to the torus, you are in the torus. Here's how it goes. If gamma is in E cross times 1 plus PD to the n, these are the elements we have to worry about. But is not in F cross times 1 plus PD to the n. If it's close to the torus but not close to the center, then gamma can be H conjugated into E cross. This gives us a beautiful structure for the conjugacy classes intersecting E cross times 1 plus PD to the n. It means that either you're in the parametrizing torus, which is where we expect character formula to look particularly nice. Remember, for example, in the Weil character formula, that's how it works. We look at the character formula on the parametrizing torus. There we don't have any option because that's the only torus there is. But if you're familiar with real group character formulas, that's how real group character formulas work. We have a parametrizing torus, and we look at the character formula on that torus. So we're saying all you have to worry about to understand the full character is to understand the character on the parametrizing torus and to understand it in this range here, which is practically in the kernel of our representation. So you're either just shy of being in the kernel or you're in the parametrizing torus. I'm going to focus on the case of being in E cross, because the other case is easier and just a little messy. I can rephrase this slightly because this result, it looks pretty innocuous. It may look surprising, but it looks pretty innocuous. But this is the real heart of why today's talk is simpler than Friday's talk. This can be rephrased as every regular element is very regular, if you know what those words mean, or for that. If you don't know what those words mean, this is saying that every regular element is very regular. And it turns out to be easiest to compute character values at very regular points. I'm not going to define it right now, but that's what this is saying. Well, I could define it. Very regular. Regular means that no roots vanish. Very regular means that you're not close to anything that's not regular. Everything nearby is also regular. And it may not quite look like it, but that's what we're saying. So now I'm going to only worry about elements of E cross, which means so far I've been measuring how pleasant my elements are by how close they are to E cross. I've measured them by are they in E cross or F cross times 1 plus power of the prime ideal, but not in E cross times the higher power. Well, now they're just in E cross on the nose. So what do I do about that? What's my new measurement? Well, it turns out the new way to measure it is to measure how close this element of E cross, how close this element of the torus is to the center. I'm going to use, and everyone is going to marvel at the consistency of my notation, I'm going to use A to measure distance from the torus and B to measure distance from the center. So if you have an element that is depth B precisely away from the center, and you try to conjugate it, by something that is depth A precisely away from the parametrizing torus. I need some restrictions on A and B here. Let me remind myself.
But that's the torus times the unit there.
No E star.
Not on the first one, no. For the purposes for which I'm going to use it, I could put an E star here and it wouldn't make the slightest bit of difference. I need some conditions on A and B, which are A is at most n minus 1 over 2, and A plus B is less than n. Under these conditions, then the sum, if I didn't give you enough letters already, if I didn't show my superior command of the alphabet already, here's another one. So the sum over elements Z at depth n minus A over B of the following piece of the Frobenius formula Now, if you look at that lemma, you'll say, my God, that's going to be awful to prove. But the funny thing about this lemma is it's actually much, much harder to state it than to prove it. Once you state it, it's obvious how to prove it. What I'm going to do is I'm actually just going to explicitly compute this commutator, or this conjugate, just like I did before. Oh, and I want H inverse gamma H in K phi. I want this H to be one of the terms in the Frobenius formula that actually lights up. So here's how it goes. We'll use A again, principle A, which is the discrete Campbell-Baker-Hausdorff. That once I perform this conjugation, you should expect you're going to see a bunch of commutators, and that's true. And the fact that I've got two conjugators here means you might expect to see two or a nested iterated commutator. That's exactly what's going to happen. My answer is up to be H inverse gamma H times 1 plus y commuted with z times 1 plus y commuted, y commuted with x commuted with z, and all this is true mod 1 plus pd to the n plus 1, which again is in the kernel of our parameterizing character. Okay, this doesn't look so pretty, but there's good news. Where, by the way, where gamma is again central element times 1 plus y, and h is 1 plus x, and z is one of these elements coming from pd to the n minus a minus b. This guy, if you commute any element of E that's not central, which is not by a restriction on y, if you commute any element of E with any other element of D, it lands in E perp. By the way, we've chosen all these depths. If you just keep careful track of things, it lands at depth n plus 1 over 2, and that means this whole term is in the kernel of our parameterizing character. Which means when I try to evaluate phi hat at this guy, I only have to worry about evaluating phi hat at this conjugate, which I don't care about at all, it doesn't depend on z, and phi hat here. So the sum is actually, that sum that I'm interested in, is actually, we can pull out the phi hat of h inverse gamma h. It's of absolutely no relevance whatsoever, times the sum phi hat of 1 plus the commutator of y with x with z. Here's my principle. Principle D, about the sum of a non-trivial character. That's the sum of a non-trivial character. It may not look much like a character, but it is. That's the sum of a non-trivial character. So by D, this is 0. Unless this character is always trivial. But we did this kind of conjugation before. Sorry, we did this kind of computation before. How can you commute with z, evaluate the character of the commutator with z, and always get a trivial answer? Well, this can only happen if the commutator of y and of x is deeper than it has a right to be. We commuted an element at depth A with an element at depth B. The most naive expectation would be that the commutator lands at depth A plus B. The only way this character can be trivial is if the commutator actually lands a little deeper, modulo E. But we also know already that the commutator lands in E perp. So it can't be close to E without being actually in this deeper filtration subgroup. So this means the commutator of y and x has to land in PD to the a plus b plus 1. But again, by the same kind of computation as before, where we look at what happens to commutators, the only way this can happen is if x is close to the parameterizing torus. But that would mean that 1 plus x, h, is also close to the parameterizing torus, and it's not. Oh. Sorry if I scared anybody. All right, so these kinds of computations are mind-numbing to the extent that you have to keep such careful track of indices. But there's only really one idea here, which is find a linear character hidden somewhere, prove that it's non-trivial, and observe that the sum of a non-trivial linear character is 0. So this allows us to drop out a whole bunch of Frobenius formula and just be left with terms where this doesn't happen. So we've now got the following formula with gamma as above. The little character value, remember this is the guy that we get by inducing up to h, not all the way up to d cross. The little character value is given by q to the b minus 1 over 2. B measures how close our element is to the parameter to the center. Times a linear character value evaluated at gamma. This is the familiar kind of thing you'd expect to see in a biocharacter formula. Times the following sum, for which I apologize, but there's no way around it. Sum over some god-awful domain of phi hat of 1 plus x times the commutator of y with x. I'm not going to go into a detailed proof of this guy. I just want to observe by the lemma, we may apply principle C of clumping together a bunch of terms in Frobenius formula. We may apply this whenever h is in 1 plus p d to the a, and not in e cross times 1 plus p d plus 1 with two a plus b less than n. Yes, sir.
Can you raise the top?
Or I could lower this guy. The top is as far up as it'll go.
Oh,
Sorry.
wait, is it? Oh, sorry.
What I've just claimed here is I can get rid of a whole bunch of terms, but I've got rid of fewer than it might seem like I'm actually justified in getting rid of. Before I could get rid of all those with a plus b less than n. Now I've claimed I can get rid of them with 2a plus b less than n. I'm not going to go into the details of it, but it turns out that if I tried to just naively apply this condition, I'd be putting some terms in multiple groups. So this just ensures that I only put each sum end in one group. I don't do some kind of nasty overcounting. Well, that means that I only have to worry about the terms where 2a plus b is at least n. And if you do the algebra, that turns out to mean I have to worry about terms that are at this depth or bigger.
What is B?
What is what?
What is B? B.
B is the thing that measures how close gamma is to the center. Less. On the other hand, you may have noticed so far, well, you may not have noticed, but the fact is that so far I've used discrete Campbell, Baker, Hausdorff in the following sense. I've used that 1 plus x is nearly a homomorphism. 1 plus x times 1 plus y is essentially 1 plus x plus y with a certain error term that you can control. That's what I call first order approximation. If you want to look deeper at that error term, the error term between 1 plus x times 1 plus y and 1 plus x plus y, the error term involves a commutator of x and y. That's what I call a second order error term, and that's where I've been spending most of my time. Now it's time for me to use a third order error term. in Campbell-Baker-Hausdorff in the following way. So if x is in p-d n minus b over 2, then the 1 plus x conjugate of gamma looks like the following, up to error terms that we don't care about. It looks like gamma times 1 plus the commutator of y and x times 1 plus x times the commutator of y and x. And all that congruence holds modulo 1 plus p dt n plus 1. Once again, this part we can ignore when we're evaluating phi hat. This part is contained in phi hat. So all we're left doing is evaluating phi at gamma and at 1 plus x times the commutator of y and x, which is just what I did up here. And the constant out front comes from the fact that certain terms are repeated with multiplicity. So this is pretty exciting. I showed you that we didn't have to worry about, or rather we only had to worry about character values on the torus, which we just computed, or near the kernel, which I haven't computed, but I think I've beaten you enough for the day. But two problems. One is I've still only computed the partially induced character. Inducing up to h, I haven't gone all the way up to d cross. The other problem is these first two ingredients in the character formula aren't going to bother you. They're a power of q and a linear character value. What about this latter guy? Well, if you stare hard enough at x times the commutator of y and x, you'll believe, or you won't admit to disbelieving, that that's a quadratic form. So what I've just done here is I've summed up not linear character values, I've summed up quadratic character values, and that's a well-known object. I'm not going to rewrite it. The messy sum is called a Gauss sum. And we know an awful lot about these guys. Its magnitude is the square root of q, and its argument is a fourth root of unity. Most of the fun of character formulas is finding out which fourth root of unity it is. It's a surprising amount of pain. And it results in things like having to describe to your colleagues what you mean when you say you're trying to distinguish I from minus I. So here's the final theorem. This is where we're going to wrap up the day with gamma as above. Full character value, big theta, evaluated at gamma can be expressed in the following way. 1 over the square root of the Weil discriminant times this fourth root of unity associated to gamma times phi of gamma plus the fourth root of unity associated to gamma bar times phi of gamma bar, where d of gamma, or just d, is the Weil discriminant. It's also the division algebra, sorry about that. And gamma bar is the non-trivial conjugate of gamma. Galois conjugate of gamma. I'm just going to say a very little bit about where this formula comes from, but first I want to point out that this is the best possible analog you could expect of the Weil character formula. It's 1 over the square root of the discriminant times a linear combination of the Weil conjugates of our parameterizing character phi, and the Weil conjugates are phi itself and phi composed with conjugation. And we don't quite get signs out front. We don't quite get plus or minus 1 as we would in the real case, but we get the next best possible thing. We get 4th root 2. Okay, so this is a very close, very accurate analog of the Weil character. How does the proof go? Well, first things first, notice that I took this sum and I called it q to the 1/2 times the 4th root of unity. I left that 4th root of unity as a coefficient and I stuck the q to the 1/2 over here, and I get q to the b over 2. And that q to the b over 2 turns out to be precisely 1 over the square root of the absolute value of the Weil discriminant. Since d of gamma, this is just a fact, is gamma minus gamma minus gamma bar squared, the absolute value to the minus 1/2, if you just compute it, turns out to be precisely q to the b over 2. So that's where 1 over the square root of the absolute value, sorry, that's where the q to the b over 2 term comes from. That's where 1 over the square root of the absolute value of the Weil discriminant comes from. On the other hand, by Frobenius formula, and the lemmas we proved above about where characters vanish and how things are conjugate, the big character value at gamma can be expressed in terms of the small character value at conjugates of gamma, where we conjugate by elements of d cross mod h, but we're only concerned with those elements that take gamma and conjugate it back into e cross. This is not the literal Frobenius formula. The literal Frobenius formula would have a lot more terms, but we showed before that most of those terms are just 0. If G conjugates gamma into E cross, then it also conjugates the multiplicative group of F adjoin gamma into E cross. But F adjoin gamma, because we're in a prime degree field, there's no intermediate field, so let alone. Conjugates the whole of E cross into E cross, which is just another way of saying that we're in the normalizer. So if we look at cosets in the normalizer of the torus, mod, well, this modding by H essentially mods out by the torus itself, we're summing over the Weil group. And the Weil group has 2 elements, and those 2 elements act on the torus by the identity and conjugation. There's a character formula for a quaternionic division algebra. That's it for today. Thank you.